Hi students, now we are going to derive an expression for the kinetic energy of a rigid body in rotational motion. Now we have many times discussed in the previous topics that when a rigid body is rotating about a given axis, so you can see here this is the axis of rotation. Now each and every particle inside the rigid body is in circular motion. Is it not about the axis of rotation at its center? So I have taken particle number 1, its mass is m1 and its linear velocity is v1 tangential to the circle, and its radius of the circular path is r1. Similarly, another particle of mass m2 and it is at a distance of r2 from the axis, its linear velocity is v2. Look at these two particles now. When the entire rigid body is completing one full rotation, in the same time these two particles of mass m1 and m2 must have completed circular motion in the same time. Okay. Out of these two particles, one is very closer to the axis, so it completes a smaller circle in the same time, while the particle number 2, which is farther from the axis of rotation comparing to the first particle. So the second particle is making a larger circle, it is completing a larger circumference in the same time. So naturally, the time taken by the two particles will be the same, but the distance travelled along the circumference will be different. Therefore, their linear velocities will be different in magnitude. In magnitude, v1 will be lesser and v2 will be greater. Is it not? So, their particles all will have different linear velocities. But what about their angular speed of rotation? Both the particles which we have considered as well as all the other particles also, when the entire rigid body rotates once, the angle subtended at the center will be 360 degree only. Is it not? All particles, irrespective of their distance from the axis, they all will have the same angular velocity. Okay, my dear students, in this concept we must remember that they all will have same angular velocity omega, but different linear velocities. Okay. Okay, now first I will take the expression for the kinetic energy of the first particle. So the kinetic energy of the first particle is equal to half into m1 into v1 square. Okay, so this is equal to half into m1 into, we have studied v is equal to radius times omega. Is it not? So the radius of the first particle is r1 into omega the whole square. V square, no, therefore r1 omega the whole square. So this is now equal to half into m1, okay, into r1 square. I will put it in a bracket, r1 square into omega square. So this is the kinetic energy of the first particle. In the same way, if you find the kinetic energy of the second particle, it must be half into m2 into r2 omega the whole square. So that is equal to what? Half into m2 r2 square into omega square. Is it not? So randomly, I will take one particle at a distance ri, so that its mass is mi. Okay, so the kinetic energy of the ith particle, so this is equal to half into mi into ri omega the whole square. So this is now equal to half into mi ri square into omega square. So for every individual particle, I have found the kinetic energy. Okay, now what is the, therefore, total rotational kinetic energy? Okay, so the rotational kinetic energy of the rigid body of the entire rigid body is now represented by ER or KER also we can write. Kinetic energy rotational. Okay. So this is equal to this half m1 v1 square plus half m2 v2 square, like that. All the particles, if I add the algebraic sum of all the terms. So this is equal to sigma half into mi ri square into omega square. So I am adding the terms mi ri square into omega square by 2 for all the particles from I is equal to, so this is I is equal to 1 to n, total number of particles. But half is a constant and omega is the same for all the particles. It is also a constant. So omega square I will take out. So this is equal to half into omega square into sigma mi ri square. What is inside the sigma term? What is it? What does it mean? It is the algebraic sum of the products of the masses of the particles and the squares of their distances from the axis of rotation. We already studied it is equal to what? Moment of inertia of the rigid body about the axis of rotation. So here sigma mi ri square is equal to capital I. So this is equal to what? Moment of inertia of the rigid body about the axis of rotation. So I can substitute capital I for this sigma term. Therefore, kinetic energy of rotation is equal to half into I omega square. So this is the required expression. We have derived an expression for the rotational kinetic energy of a rigid body about an axis. Okay, look at the terms. Is it similar to that of half mv square in translatory motion? So, kinetic energy in translatory motion. We have already studied that this is equal to half into m into v square. So, can you understand that the rotational analog of mass is moment of inertia and the rotational analog of linear velocity is angular velocity. So these are similar terms only. Okay children, now you tell me, have you derived an expression relating kinetic energy and momentum in translatory motion? In the same way, we are going to derive an expression relating the rotational kinetic energy and the momentum, angular momentum. So the next one is relation between rotational kinetic energy, that is kinetic energy rotation, and angular momentum capital L. Okay, so this is the next derivation in very simple terms. We have already studied that the kinetic energy in translatory motion is equal to P square by 2m. I will write here. Okay, so in translational motion, first of all, we will recall. Okay, in translational motion, we have studied that kinetic energy is equal to P square divided by 2m, where m is the mass of the body and P is linear momentum, which is what? The product of mass into velocity, is it not? So in the same line you think, in place of P square we have to write what? L square, and in place of 2m we have to write 2I. Then the left hand side will become rotational kinetic energy. That expression we have to derive now. Understand? So now you can see here this term, kinetic energy of rotation is equal to half into I omega square. I will start with that. So kinetic energy in rotational motion. Okay, so this is equal to half into I omega square. Okay, now I will multiply once again by capital I and divide by capital I. So this is equal to half into I omega square divided by I. So this is equal to I square omega square divided by 2I. So this is equal to I omega the whole square divided by 2I. So left hand side is what? Kinetic energy rotation. Okay, you can write Ke also, no problem. E rotation also is correct. So I omega is equal to what? L. This only is equal to what? Angular momentum. Therefore, we have proved that the kinetic energy in rotation is equal to L square divided by 2I. So this is the expression relating the rotational kinetic energy and angular momentum. I told you first itself, is it similar to that of P square by 2m? So instead of P square here, it is replaced by L square. And here 2m is replaced by twice I, where I is the moment of inertia. And this expression is extremely important to solve the numerical problems in most of the competitive exams. Repeatedly they are asking numericals from this. Practice that. So my dear students, I am repeating once again, in rotational motion, each and every particle other than the particles at the central axis, all the other particles will have two types of motion. Understand? So they will have two velocities. One is linear velocity, the other one is angular velocity. Okay? So now they will have a kinetic energy. If you add the kinetic energy of all the particles with respect to the axis of rotation, what you get is called the rotational kinetic energy of the rigid body. So finally we have derived the kinetic energy of rotation is equal to half I omega square. Then we have derived the relationship between kinetic energy of rotation and angular momentum, that is given by rotational kinetic energy is equal to L square by 2I. I hope you must have understood well. Fine.